Hello students, this is our lecture on water and why water is such a big deal. So every once in a while you hear a story about how, oh, there's evidence that maybe there was water at one point on Mars, or there's water in the tails of comets, so possibly there's life there. Uh, the constant search for water on other planets. Astrobiologists and biologists and the NASA people at NASA always get up in a tizzy every time they think that there may be the possibility of water on another planet. And the reason is because water has several properties that make it a truly unique substance and make it vital for life. Water is an absolute necessary component for life. And today we're going to take a look at why. What is it about water that makes it such a big deal? It's something we completely take for granted. We turn on the faucet, it's there. We use it to cook and to clean. Here in Minnesota, we have an abundance of fresh water with all our lakes for recreation and swimming uh, and fishing and boating, and the list goes on and on and on. Uh, it's something that we take for granted because we have so much of it around us. Um, it is a truly an amazing substance. Let's delve into why it is that water is so important to life. All right, so there's our big idea. Water has several properties that make it a unique substance necessary for life. I don't have a handout for you, so we're going to do some note taking. You can just title it Properties of Water. As you watch this, if I'm going too fast, you can pause it to jot down what you see on the screen. I've got a whiteboard behind me. At some point during the lecture, I'll change camera views and I'll do a little illustration on the whiteboard. And I recommend highly that you write that stuff down as well. Bury that in your notes. And follow the note pattern that I follow. If I indent, if I underline or skip a space or put a little dash, do those things too. That information, that setup helps you keep the information organized on paper, which helps it keep the information organized in your brain. All right, let's keep going. All right, so what is it about water that makes it so special? All right, so several properties. One, it's polar. It has an uneven distribution of electrons in a molecule. Right. So, what does that mean? Uh, Water looks like uh, a little Mickey Mouse. It's got one big oxygen and two little hydrogens, and the two hydrogens are bonded covalently to the oxygen. So that means that they share those electrons, and um, uh, it's a strong bond, so it's hard to break the hydrogens off of the oxygen. But it's a polar bond, which means that the electrons are not shared evenly. Again, I'll illustrate on the whiteboard behind me why that is the case in just a little bit. But what this means is that the oxygen has a slightly negative charge compared to the hydrogen, which has a slightly positive charge. This creates this phenomenon called hydrogen bonding. So from physical science, maybe we need to review, but you may remember there's different kinds of bonds. There's ionic bonds, and that's where one electron is taken and one molecule takes an electron, another molecule, one element takes an electron, one element gives up the electron. Um, there are metallic bonds, bonds between the elements that are metals, and there are covalent bonds. So these are the bonds where the electrons are shared, and these are stronger than ionic bonds. Well, we also have hydrogen bonds. And hydrogen bonds is the attraction between the hydrogen end of one water molecule and the oxygen end of another water molecule. Right, so what does that look like? All right, so these bonds are weak, but they're effective. All right, so here's this illustration of water. This is important. So here's our oxygen molecule. Here's our hydrogen molecules, atoms. Notice that it's not a straight line. The oxygen, this is actually a measurable degree. I think it's 109 degrees. The angle between the two nuclei of the hydrogens and the nuclei of the oxygen. The point is that it's slightly bent like this. This means that there's a negative charge here on the oxygen and a positive charge here on the hydrogen. Well, polar bonding is when a hydrogen of one water molecule is weakly bonded to the oxygen of another water molecule. And we'll see pictures of that. So here's our positive end, here's our negative end. All right, so here's an illustration of some hydrogen bonding. So these positive hydrogens are weakly attracted to this oxygen. And this positive hydrogen is weakly attracted to this oxygen, and this positive hydrogen is weakly attracted to this oxygen. So these bonds, they're weak. They're not strong like a covalent bond or an ionic bond. But what that means, as weird as this sounds, is water is actually sticky. Water wants to stick to itself, and water wants to stick to other things. And it's because of this hydrogen bonding. It's because of this hydrogen bonding and this shape of water that it's got this positive end and this negative end that it behaves in such a unique fashion. One example is water, to the best of my knowledge, is the only substance on planet Earth that exists in all three states: solid, ice, liquid, water, and a gas, clouds and water vapor. It's the only substance that exists in all three of those states on planet Earth at the same time. Pretty cool. All right, so cohesion. Cohesion is the attraction between molecules of the same substance. So co meaning together, water wants to stick to itself. Again, because of that hydrogen bond. What this creates is surface tension. Water is sticky, so water has this surface tension. Water also wants to stick to other things, and that's what adhesion is. Adhesion is the attraction between molecules of different substances. Now, you've seen this phenomena demonstrated many times. You probably haven't thought of it as cohesion or adhesion. That's precisely what it is. Think of a straw. If I took a straw and I stuck it in a glass of water and I put my finger on the top of the straw so it creates a vacuum, when I lift that straw, there's water in that straw. Well, the water wants to stick to itself, so the water molecules in the straw want to stick to itself, and the water molecules also want to stick to the side of the straw. Or if you've ever had blood drawn, you poke your finger, and then the technician takes this really skinny glass straw, and they put it on the end of your fingertip where the blood is coming out, and the blood just rushes up the straw. Well, that's because of the cohesion and the adhesion of water. Your blood is mostly water. So the adhesion part is the water molecules sticking to the glass and literally pulling itself up that little tiny narrow straw. And the cohesion is the water molecules sticking to each other. This is how a tree gets its water. Think of a 150-foot oak tree in your backyard. The water goes down into the roots, and it somehow makes it up to those leaves, 150 feet above the ground. Well, how is that happening? It's the process of cohesion and adhesion. The water inside the roots, because there's tiny, tiny, narrow tubes inside of a tree, and those narrow tubes is like that narrow glass straw when you're having blood drawn. The water naturally pulls itself against the force of gravity up those tiny, tiny, narrow tubes and makes its way all the way to the top. Water droplets sticking to leaves, or water droplets sticking to a can of pop outside on a hot day. Here's an example of cohesion, right? You can see the little dips in the water. That's the water sticking to itself. And here's an example of really both cohesion and adhesion. The droplets form because of cohesion. The water molecules stick to each other, and they stay on the blades of grass because of adhesion. They want to stick to other things. Again, this has profound implications at the level of the cell with respect to how water moves in and out of a cell. All right, so capillary action. I already started talking about this a little bit. This is the tendency of a liquid to move up a narrow tube as a result of adhesion and cohesion. water moving through a tree trunk. Water also has a tremendous heat capacity. All right, so what does this mean? This means that it takes a lot of energy to heat up water. Well, why is that the case? Again, it comes down to these hydrogen bonds. In order for water, temperature ultimately is a measure of movement. The faster molecules are moving, the higher the temperature. All molecules are always moving. Even the chair you're sitting in, the desk you're sitting at, the molecules in that chair and in that desk are constantly moving. It's just in water, they're moving a little bit more, and in liquid, or in a gas, they're moving even a little bit more. As something heats up, those molecules move around faster. Well, that's an increase in temperature. Well, in order for those water molecules to move around faster, we have to break those hydrogen bonds. So all that energy that goes into breaking those hydrogen bonds is what causes the water molecules to move. Think about boiling a pot of water. It takes a long time. You throw 4 cups, 5 cups of water in a pot to make you macaroni and cheese. It takes a long time for that water to heat up. Right? So what does this mean with respect to life or life on the planet? Well, your body is like 80% water. But being alive is a really dizzyingly complex, never-ending series of chemical reactions. All chemical reactions generate heat. That water absorbs that heat. Right? The reason that cells don't overheat in order as chemical reactions happen to keep them alive is because the water inside the cell and outside the cell absorbs a lot of that heat and regulates the temperature of the cell, by extension regulating the temperature of the tissue, and then regulating the temperature of the entire organism. On a global scale, the oceans are giant radiators. They control and absorb tremendous amounts of heat from day to day as the sun comes up and goes down, but also from season to season. The water heats up during the summer, cools down during the fall. So water has a tremendous heat capacity. It takes a lot of energy to raise the temperature of water, which means that it's a really good buffer for absorbing heat. For you gearheads out there, think of a car. Yes, we put antifreeze in a car. It's a chemical called ethylene glycol in the radiators, but oftentimes we'll mix water with it. And that's because we mix the ethylene glycol to keep the water from freezing. But as an engine is running, it generates a tremendous amount of heat. Well, what we do is we run water around that engine, and that water absorbs a lot of that heat, keeping that engine cool. Oh, I'll get this sign out of there in a second. That states water can absorb a lot of energy with a little temperature change. Again, that can happen on a global scale, or it can happen on a much smaller scale, like the level of the cell. All right, so let's talk a bit about mixtures. A solution is a type of mixture in which all of the components are evenly distributed. This would be like if you put Kool-Aid in a glass of water and mix it up. That's your lemonade or your Kool-Aid. Eventually, those particles get evenly distributed. That's the solution. The solute is what gets dissolved. The solvent is what does the dissolving. Water is sometimes considered the universal solvent, not because it dissolves everything, but because it dissolves a lot of things. All right, so there it is right there. All right, so what's a suspension? A suspension is mixtures of non-dissolved particles. Suspension is a mixture of non-dissolved particles. Like if you put a bunch of pebbles, rocks, and sand inside water, that stuff doesn't get dissolved. Okay, so take a look at this drawing, and if you need to pause it, by all means, certainly go ahead. Here's a chunk of salt. A salt is salt, like table salt. It's made up of sodium and chlorine. All right, so it's an ionic bond. The sodium gives an electron away to the chlorine takes an electron. Because electrons are negatively charged, there's an extra negative charge on the chlorine, hence it's negative. There's an extra positive charge on the sodium, so it's positive. When sodium and chlorine are together, they're neutral because we have the positive and the negative that cancels each other out. But when we drop that into water, what ends up happening is the salt starts to break apart. The big salt crystal starts to break down into the individual smallest bits of salt, which is one sodium and one chlorine. And then what happens is those sodiums and chlorines actually come apart. All right, so take a look at this picture. Here's the big chlorine. Remember, the chlorine is negatively charged. Well, look at all these positive hydrogens that are stuck to this chlorine. Again, the hydrogens are positive. They're attracted to the negative of the chlorine. And then look at this look at this sodium. The sodium is positive, so the sodium's the little one. The sodium has a positive charge. Well, water, the oxygen of water has a negative charge. So there are several oxygens weakly bonded to this chlorine ion. Well, that's what it means to be dissolved. Like we put salt in a glass of water and whoa, it's magic, it's gone. Well, but we can still taste it. We know it's still there. Well, you can taste the individual sodiums, you can taste the individual chlorines, other way around, the individual chlorines and the individual sodiums. But like literally, this chlorine can't touch that sodium because they're physically blocked by the water molecules that are stuck to them. This means that water can dissolve substances. A cell can dissolve substances like salts and sugars and positively and negatively charged particles. Again, I'll draw this on the board. I want you to draw this before we end the day. All right, lastly, a little bit about acids and bases. What do we mean when we say something is acidic or when something is alkaline? All right, so here's our water, oxygen, hydrogens. Sometimes, if you have just pure water, a tiny bit of that water, what ends up happening naturally is it breaks apart. It's called dissociation. It only happens in a tiny percentage. What happens is some of the water molecules split and form ions. So within a glass of pure water, you will have some hydrogens. So here's a single hydrogen, and then this other thing called a hydroxyl group. You don't need to know that name, it's not important, but it's an OH, right? So in pure water, most of the water is this, straight up H2O. A tiny percentage is this dissociated water, which is this hydrogen and this hydroxyl. Because it's pure water, no matter how much of this individual water molecules break apart or dissociate, because it's a 1-to-1 ratio, in pure water, the amount of free-floating positively charged hydrogen and the amount of negative floating charged OHs is the same. An acid or a base is something that has more of one and less of the other. Right, so water molecules sometimes split and form these ions. Here's water. Sometimes some of this water splits into this hydrogen and this hydroxide. Now notice this hydrogen loses the electron and this oxygen takes the electron. So right now this thing is literally just a proton. I don't know if you remember this from physical science, but sometimes in the conversation of life and in biology, sometimes pure positively charged hydrogen is referred to as protons. Hydrogen is number one on the periodic table. That means that it has one proton and one electron. What's weird about hydrogen is it doesn't have a neutron. All right, so, and that's why we can call this a proton. Anyways, here's a positively charged hydrogen, negatively charged OH group called the hydroxide ion. An acid is something that has more of this than this. And a base is something that has more of this than that. All right, so what is pH scale? pH is a measurement that indicates the concentration of hydrogen ions. No one really knows what pH stands for. I like to think of it as percent hydrogen. That's not what it stands for, or I think sometimes I like to think of it as parts hydrogen, meaning how much of this hydrogen is actually in a system. Right, so that's the pH scale. Right, so if something is acidic, the scale is from 1 to 14. If something is acidic, that means that it has a pH of less than 7. All right, that means that there is anything that has a pH of less than 7, there's more of this than there is of that. Anything that is a base is called, sometimes referred to as alkaline, and that has a pH scale greater than 7, which means that a base has more of this than that. Water is not an acid or a base. Right? Water is 7. So the scale goes from 1, which would be a really strong acid, to 14, which would be a really strong base. 7 is the middle. Now, why it's a scale of 1 to 14, that's fairly complicated chemistry that we don't get into. Take AP biology, and you'll have to know that very well. But for now, all we need to know is that it's a scale of 1 to 14. Anything below 7 is an acid. Anything above 7 is a base. Well, lots of chemical reactions form acids or bases. Water, pure water, has that pH of 7. Water is a buffer, which means that water can take acids and make them neutral, and it can take bases and it can make them neutral. Sometimes chemical reactions produce acids or bases, and if those acids and bases don't get neutralized, they can cause problems. All right, so neutral, equal number of hydroxide and hydrogen ions. Buffers are weak acids or bases that react with strong acids or bases and prevent sharp, sudden changes in the pH. Right, so water, while it's not a weak acid or a weak base, is a very powerful buffer. Right, so a good example. We breathe in oxygen, we breathe out carbon dioxide. That carbon dioxide comes out as gas, but the carbon dioxide has to travel through your blood in the form of dissolved carbon dioxide. Well, dissolved carbon dioxide forms in your blood, forms carbonic acid. So if water wasn't in there, that carbon dioxide would stay as carbonic acid, but the water helps neutralize that CO2 so the carbonic acid doesn't build up in your blood. Again, you don't need to know that for a test or anything. It's just an example. Just about done here with the slides. I'm going to skip that. I'm going to skip that. We don't need to worry about that. And we don't need to worry about that. All right. I believe that is it. Okay, so let's end there with the notes on the water. What I'm going to do is I'm just going to change cameras here. I'm going to plug in, excuse me, I'm going to plug in a different camera. And now our view should change. All right, so I'm going to go like this, and like this, and like this, and like this. Bear with me here. Let's go to camera. right, I'm gonna have to do some editing here.